Hi, this is Professor Hiley. Just wanted to give my class a little video about how to how to formally show that a limit exists and that it is a certain value. This is from section 2.7 in the textbook, and I want to highlight with some specific examples how to do that. This is for you to know how to show what work you need to show on the test when you take it, what I'm looking to see. And I was looking for some videos online like I have done with some other things, and wasn't really quite satisfied with what I was seeing. So I'm doing this for you myself to help you understand the topic. Okay? What we're looking at is, I have three examples that I'm going to show you, and I'm going to kind of show you two ways. I'm going to show you visually what's going on with the graph, and then I'm going to show you what calculations that you need to do to show that a limit is in fact what it is claimed to be. So the general steps that are involved when we want to show a limit is first thing that we do is we choose what the book calls an epsilon greater than 0. Now what does epsilon mean here? It means that whatever limit that you think that is believed to be the correct answer, epsilon represents a distance from that value. So for example, looking at this first function, we know from the limit laws earlier in the chapter that the limit of 2x as x approaches 2 is 4. These are the ones where in this case, you can plug in, right? Because 2 times 2 would be 4. So we believe that to be true, but we want to formally show that that's the case. And so just for an illustration, I have three functions that I want to do this for, because I want to show you exactly what's happening and why we're doing what we're doing. So when I say choose epsilon greater than 0 over here, on the graph here for 2x, I'm going to pick epsilon equal to 1. The only reason I'm doing that is because it's big enough for you to see in the video. Not because I have to choose epsilon equal to 1. So epsilon represents a window, right? And so this would be 4 plus epsilon up here. This would be 4 minus epsilon here. Okay, so we choose an epsilon, and I'm just drawing it big enough for you to see. And so we choose an epsilon greater than 0. And then what we're going to look at is we're going to consider this window, f of x minus our proposed limit, and we less than epsilon. We're going to look at this window. And that window is exactly, in this graph, it's exactly this bar right here, okay? So we want to look at that window there. And then ultimately, what do we want to do with that? Well, these formal definitions are given an epsilon. We want to find the delta. So I'm going to use a different color here because I want to highlight something with colors. Okay, so in this case, right, just be clear in the graph, our limit is 4. So the L here is 4. What is this x naught here that I'm talking about? The x naught is the 2. So in this case, this is 2, right? Over here, 1, 2. And that represents our x naught. Okay. So the idea, graphically speaking, is this. That I'm looking at this window right from here to here, and what I want to do is I see where it hits the graph, and I find a window down here. Okay, and what do I mean by this x minus x naught? I mean right down here, that there's a window here, so this is x naught. This value right here would be 2 plus delta, and this would be 2 minus delta. So the idea of these exercises is, given this kind of window, you want to find a mirror image window down here that matches it. And you want to identify this distance in terms of this distance. Okay? This distance right here. So you want to match that up. And I'm going to do that with each of these problems. And what we're going to find is that I've got 3 examples here. I've got a line, I've got a parabola, and I've got a square root function. And what I'm illustrating is that we'll see here in this line that we have an even window here, and you get a matching even window down here. But we'll find out when we do these functions over here that the window that we get down here isn't even on either side. And so we're going to have to choose delta a little more carefully. So I'm going to now go ahead and do the math that would be involved, do these steps that I've highlighted right here so that we can see how it looks for each of these problems. Okay. All right, so as I said before, we choose epsilon greater than 0. That's how you always start these things. And then we want to assume that we're in the window. So our proposed limit here is 4. And our f of x in this case is 2x. And you'll see that the line is nice and easy here, that this is going to be easy to do. So this is where we always start these things. We start with our function, which the function is always spelled out. That's whatever you're finding the limit of. And then your limit, the number that goes here is always whatever you think that the limit is. And we start with this, that corresponds to that. And now we want to come down here and find this x minus x naught. Now in this case, what we're interested in, our x naught is 2. And so what we want to go from is we want to go from this expression and we want to somehow get to x minus 2. Well, in this case, because it's a line, there's an easy way to do that. In this case, we can just factor the 2 out. So we could say we could transform this by factoring a 2 out, and we could say that that's, of course, less than epsilon. And again, what are we interested in? We're interested in x minus x naught. So we need to get rid of that 2. The easy algebra here is to divide both sides by 2 then, and we get that x minus 2 is less than epsilon over 2. And this is exactly what we were looking for, because now we want to choose our delta, okay? And so in this case, this is not the proof. This is the kind of scratch work that you do to prepare yourself for the proof. And so let me show you then how the proof then would look. So the idea here is that once you're able to get this form, you're going to let this be delta. So we're going to let epsilon over 2 equal delta. So now I'm actually going to write the proof part of it, this, now that we've done the background work that we need to do. Okay. So the proof would go like this. So I'll write PF up here, short for proof. And the proof goes like this. So you let delta equal what you want, what you know it needs to be. Okay, and that's why we did this work, to figure out what delta needs to be. And then show that that actually works. Okay, so for example here, so instead of starting with let epsilon be greater than 0, I'm going to start, we understand that, right? That's a given. I'm going to let delta equal epsilon over 2. And I'm going to write what I did here pretty much backwards. And that's actually how you show the proof. So we have, so that means I'm going to let x minus 2 be less than epsilon over 2. And so I'm literally walking this up backwards. I'm going to multiply both sides by 2. And then this right here is the proof. Okay, so you do some, the way these go is you do some scratch work at first, you find out what your delta needs to be, and then you're going to literally write backwards what you wrote as a proof. So you're saying that you tell me how close you want to be to, the idea here is this, you tell me how close you want to be to 4, and I tell you then how close you need to be to 2 to get as close as you wanted to be to 4. So for example, say you wanted to be within 1/10 of 4, right? So suppose you wanted epsilon to equal 0.1. This is supposed to work for any epsilon greater than 0. My answer to you, how close do I need to be to 2 to get that close to 4? My answer is delta would equal 0.1 divided by 2, or 0.05. So what I'm saying there is if you're within 0.05 of 2, you're going to get within 1/10 of 4. And if you want to get closer, I can still give you a number. Forever, how close you want to get to 4, and that's the idea of limits. Limits are the idea of getting close, right? And so you can tell me as close as you want, and I can tell you how close you need to be to get as close as you would like. And so that's the proof there. Now, let's take a look at this one. This function is not linear. And what we're going to see here in these next two examples, that when the functions aren't linear, like that one was, then we're not going to be able to, then the window we get on the bottom is not going to be equal on each side. And we're going to have to choose delta, the right delta, a little more carefully. So I'm going to illustrate with this example here. The limit as x squared of x squared as x goes to 2 is 4. And again, this is one we know from the limit laws that you're allowed to plug in this case. So we know that this should be the correct limit. And but we're just using this to prove formally that this is the correct window. So again, I'm going to choose an epsilon greater than 0. Grabbing my colored markers here to do the same illustration. And again, I'm just going to go with a window of epsilon equals 1, not because I have to, but because it'll, it's just for visual sake so you can see it. So here's my window, same window. Okay, and we want to show then that the window we get, the corresponding window down here. Let me highlight that. And what I want us to see is that the window here isn't equal on either side. And so when we pick delta, we'll need to be careful. And I'll show you the calculation of exactly how to do that. A lot of other videos kind of have you take a fudge guess. I'm just gonna have us calculate directly. So we're going to do the same thing here where we do our scratch work. We're going to choose epsilon greater than 0. And again, my function is x squared. My limit is 4 still, right? And I want that to be less than epsilon. And ultimately, what I want to do is I want to say something about x is supposed to be going to 2. So ultimately, I would like to say something about x minus 2. Now, how do I do that? Now, a lot of other videos, a lot of other examples, they'll have you try to factor this. I'm not going to have you do that. We're going to just solve it directly. And I'm going to show you exactly how to do that, because we don't need to make, what they do is have you factor it and make a clever guess. But we don't have to make a clever guess in this case. We can actually solve directly. And so here we go. So the first thing we're going to do is, it's not like the linear one where we can just factor a number out and we're happy. So what we're going to have to do is we're going to have to pull these absolute value signs. So x squared minus 4 less than epsilon means that x squared minus 4 is between positive epsilon and negative epsilon. Okay? So whenever you have an absolute value less than a number, that means it's between plus or minus that. Okay, that's just an inequality fact. Okay, and then I'm going to solve this for x. So I'm going to say that x, so that means I'm going to add 4 to both sides. So I'll get x squared is between 4 epsilon and 4 minus epsilon. And again, that was found by adding 4 to each of these things. And then, again, I don't want x squared, I want x. So I'm going to take the square root of both sides, of everything. So what I'm going to have here is the square root of 4 minus epsilon is less than x is less than the square root of 4 plus epsilon. Okay. But what do I want? I want x minus 2. Okay. So I need to subtract 2. So I'm going to come up here, draw a little arrow, and I have the square root of 4 minus epsilon minus 2 is less than x minus 2 is less than the square root of 4 plus epsilon minus 2. Okay? So I'm almost there, because what I was interested in is x minus 2. Now here I pointed out earlier that this window down here is that the sides are not equal. And where you can kind of see that when you're doing the algebra is you can see that this and this are not quite the same thing, right? You see the 4 minus epsilon there, you see a 4 plus epsilon. That means they're not exactly the same thing. So, okay, what do I need to do then? Because I want to pick a single value of delta. I'm not looking for delta 1 and delta 2. I'm looking for a single value of delta. What we need to do is we need to choose, find which of these two has the smallest absolute value. Okay? So there's a couple ways that you can do that. So we need to choose the smaller. absolute value. One way to do that is to simply plug in a number. Okay? I told you guys, for example, here that I picked an epsilon of 1, right? And so, so one way that you can do this is choose an epsilon, and then see which one has the smaller absolute value. Okay. So my example is I let epsilon equal 1. Well, if I plug in 1 there, right, I'm going to get the square root of 3 minus 2. If I plug in 1 here, I'm going to get the square root of 5 minus 2. And then what I would do is I would use my calculator, and I would figure out which one of these had the smallest absolute value. So in other words, this one's going to be negative, right? And this one's going to be positive, because square root of 3 is less than 2. Square root of 5 is bigger than 2. So this will be negative and positive. I'm not worried about the sign. I'm just worried about the size of the number. And whichever one turns out to be smaller, that's the one that I'll pick for delta. Okay? So if we do, I think this is like 1.732 minus 2. And this is, if I'm remembering right, like 2.26 minus 2, right? I'll have to double check that with my, but we could verify which one of these two is smaller, and then you go with that. Okay. So then I'll just, for right now, I'll say choose delta equal the smaller of the two. Now, I can figure out algebraically which one's the smaller of the two. The way that I would do that would be to multiply this up and down by the conjugate. And so I'm not going to do the work there because I'm thinking that, but I will show you the answer. This one, and that way I'll know which one of these is smaller without having a calculator in my hand at the moment. This one is, if you multiply up and down by the conjugate, because, you know, it's never satisfying unless you have the right answer, right? And so, and looking, if you multiply up and down by the conjugate, which this, by the way, is the conjugate of that, this is the conjugate of that, we see they have the same numerator, but we see that his denominator is bigger, right? Then because he's a plus and that's a minus, the minus would make that smaller. So what's going to turn out is that this is going to be the smaller of the two, right? So, and probably if we check numerically, the square root of 5 minus 2 is smaller than the square root of 3 minus 2. So this would, I will let delta equal this one. And because one's plus and one's minus, to be on the safe side, you can always say the absolute value, because you don't want, delta is supposed to be positive. So there it is. This would be the delta that I would choose, and so I would let delta equal this, and then I would literally write this backwards and come back to this to show the proof. Just like I wrote that one backwards, I would literally reverse my steps. So my proof would say epsilon is greater than 0, and then I would literally reverse wrote what I wrote here. That if I pick my delta equal to this, that I can then figure that out, okay? And again, I can use this function that if you tell me how close do I need to be to 4, if I want to be within 0.1 of 4, right, then what delta should I pick? I should pick the square root of 4.1 if I want epsilon to equal 0.1, then I need delta to equal square root of 4.1 minus 2. I could do the calculation and I could figure out what number that needs to be. So that's this example right here. Okay. So I'm going to erase because I need some more space over here because I've got one last problem to show you. Okay. So again, I have the same thing. I want to pick the window. Around 2. So this would be the upper window, right? And this would be, so I want to go 1 above, I should say, and 1 below, right? And in this case, the 1 below hits over here, okay? So my window is actually, so my delta window, since it's to the left here, my delta window is actually going to look like this. So it's going to look like that, right? And we're centering about this window right here. We're measuring from here to here and from there to there. And again, we want to choose the smaller of the two. That's the idea. Same setup. So in this case, the absolute value of the square root of x plus 2 minus 2 is less than epsilon. Again, this is my scratch work. I want to figure out what delta I need to use for my proof. And so then I'm going to just do the math here. So again, this isn't like that nice line where I can just factor out a number. So I got to actually pull the absolute values. I'm going to add 2 to both sides. And now I want x, so I'm going to get rid of the square root. So I'm going to square everything. So I have 2 minus epsilon squared is less than x plus 2 is less than 2 plus epsilon squared. I'm not expanding it out. I could. I'm just trying to save some algebra steps here and save some time. But I don't want x isn't approaching negative 2. Again, what am I interested in here? X is approaching 2. So I'm interested in x minus 2. So I don't want plus 2, I want minus 2. So the step I need to do there is subtract 4 from everything. So I get x minus 2. So I get x minus 2 is less than 2 minus epsilon squared minus 4, 2 plus epsilon squared minus 4. Again, this window is not equal. These are not quite the same thing. So I need to pick, like I did over here, I need to pick the smaller. So again, what's a way that I could do that? I could choose a value of epsilon and see which one's smaller. So let's say I let epsilon equal 1. Same thing. This will be easier to see than the other one was because there's no square root here. So I'm comparing 2 minus 1 squared minus 4, which is negative 3, and 2 plus 1 squared minus 4, which is 5. Which one has the smaller absolute value? Well, 3. Right? It has a smaller absolute value than 5. So that's telling you that I want to pick that one. That's the smaller one. So I'm going to let delta equal the absolute value of 2 minus epsilon squared minus 4. And again, this is not the proof. This is telling me the depth, the value of epsilon I need. and then I would literally reverse the steps to write the proof of what I was doing over here. So I hope this helps as kind of what I'm looking for. You're looking for that delta, and when you have a line, you just factor out a number and you're going to find one value. If you got a curve, then it's not going to be an equal thing, and you've got to find the smaller of the two, and you can do that by simply plugging a number in and see which one is actually smaller, and that'll tell you. Okay? So thank you very much. I hope this helps. I'm glad to have you guys, and I hope you're having a good semester. Thanks.